Hi everyone, welcome to My Max Academy. In this video, we'll continue with the chapter Relations and Functions, which is your first chapter from your 12th standard CBSE Mathematics. I will continue with example 26 in your textbook, page number 16. So the question is, or what is given in the question is, in example 26, given is f is a function from n to n, set of natural numbers to set of natural numbers. Again, g is also a function from n to n, and h is a function from n to r, set of all natural numbers to real numbers. Given by f of x is 2x, g of y is 3y plus 4, and h of z is sin z. Right? So the three functions given and the definitions are given. Now we need to prove that h of g of f is equal to h of g of f. So basically we need to prove that this function is equal to this function. Again, it's a composition of three functions, h, g, f, h and g, and basically this is the associative property of composition of functions, and it is true that the composition of functions, they satisfy associative law. Right? What is associative law? For three functions, your h of g of f is equal to h of g of f. Right? So now we are going to prove this for this particular three functions. In general it is true. So obviously in specific for this particular functions also it will be true. That's what we are going to prove now. So proof is, let's take the LHS. LHS is what? H of g of, so what is h of g? So how do we read this? This is h of g of f that we need to find. That is on x. H of g of f of x. We need to find what is this function. That is defined as h of, right? H of h of, we'll write it as g of f. G of f of x. Clear? Right? So what is h of? That is h of g of f of x. Now that is equal to, h of means which h, then you have to put the bracket, h of g of f of x equal to, and that is equal to, I can write here, that is equal to h of, now g of f is g of f of x. That is equal to h of g of, now what is f of x? F of x given as 2x. So it becomes g of 2x. Because your f of x is 2x. So I am substituting in the place of f of x, I am putting 2x. Right? Now, again that is equal to h of, what is g of 2x? G of y is 3y plus 4. So if it is y here, I have to put y here, but in the place of y, I have 2x. So wherever y is there, we have to put 2x here. So which becomes 3 into 2x plus 4. That is 3y plus 4. Your g of y is 2x. So 3y plus 4. So you have to think this as a y and substitute here. 3y plus 4. Right? That is equal to, you get h of 3 into 2 is 6x plus 4. That is equal to, now what is h of x? H of z is sin z. See, as I said, the variables don't matter. Variables don't matter. We can use different variables. See, if you have a function, suppose if I have a function f of x equal to x or anything, x square, then we can also say f of y equal to y square. Both are same, one and the same. Just any variable we can use to define the function. Right? Now this is h of, you think this as z or z, h of z. H of z is what? Sin z. So this becomes sin of z. Z is 6x plus 4. So this is your h of g of f of x, that function. Clear? Now let's find the LHS, RHS. We have found the LHS. This is your LHS, left hand side. Now let's take RHS. So what is RHS? H of g, that is our RHS. H of g of f of x. The function should operate on the element. Right? Now what is that? So x is any number. So that is equal to h of g of x. So this is of f of x, right? So we have to do this first. This is together. So h of g of x. So this h of g is operating on f of x. So that becomes, now this is h of g of f of x. This becomes h of, now h of, when you say of, this bracket, you have to remove this o or 0, whatever you call it. This is o, h of g. So h of means I should put a bracket g of f of x. Fine. So that becomes h of g of, again what is f of x? F of x is 2x. So it becomes 2x. Probably I'll put this first here. Probably I'll write this first. So this is equal to h of g of what is f of x? F of x is 2x. So I can put that 2x here. Then we should find what is h of g of 2x. So that is equal to h of g of 2x. Right? Now what is that? That is equal to h of, what is g of 2x? Your g of 2x is 3y plus 4. So it becomes 3 into 2x plus 4. So 3 into 2x plus 4. Because your g of y is 3y plus 4. So your g of 2x will be 3 into 2x plus 4. And so that becomes h of 6x plus 4. Now that is equal to, now what is h of z? H of z is sin z. So you think this as z. So this becomes sin of 6x plus 4. So that is your h of g of f of x. Now both these two are same. So this is your h of g of f of x is equal to this, and h of g of f is also sin of 6x plus 4. Both are equal. Therefore these two are equal. And this is true for every x. This is true for where x is coming from the set n. So it's true for every x. For every x. So this is true for every x belonging to n. Every x belonging to where it comes from, set of all natural numbers. This x comes from this natural number because the first function here is f. The domain of this will be the domain of f. Domain of f is x. For every x belonging to n, here also x belongs to, for every x belonging to n. This is also for every x belonging to n. Therefore both the functions are equal. Therefore we can say h of g of f is equal to h of g of f. So both are equal because both are giving you sin of 6x plus 4. This is also sin x. So for these two are equal, then we need not put the x there. We can just write without x, which means they are saying this function and this function are equal. They have become equal functions. Correct? So this function is equal to this function. So it is, in general, it is true. Like it is what? It is this associative law for composition of function. And composition of function satisfies associative law. Fine. Now let's go to the next one, which is theorem 1. Theorem 1 is again it's associative law. I'll draw the line here. So theorem 1. So what it says, theorem 1, in the same page 16 after the example 26, it says f is a function from, so given is f is a function from x to y, and g is a function from set y to set z, and h is a function from, put z, h is a function from z to s, are functions. Then we have to show that what we have to prove, f is a function from x to y, g is a function from y to z, h is a function from z to s. Now to prove in general, we have to show that h of g of f is equal to h of g of f. So again we'll have to prove similar relation. So here we proved for a particular function, here we have to prove for any three functions. Any three functions, the associative law for composition of function is true. Right? So now let's do this. Let's try to find the LHS. So proof is h of LHS is h of g of f is operating on x. That is defined as h of g of f of x. So first this h of, you should treat this as two functions. H of, this is one function, h of g of f. So that is h of means you have to put the bracket, then this o will go away. This o you will replace it with bracket, then is equal to this, and again that is equal to h of, now g of f of x is written as g of f of x. Fine. So that is what we finally get. Now again it is true for every x. It is true for every x belonging to this x. Because this x that we are taking, it is coming from the set x, capital X, which is the domain of f. Domain of f will become the domain of h of g of f. Domain of f will become the domain of g of h of g of x. The domain of f is same as h of g of f's domain. For this set also the domain is x. So this set is, sorry, this function, I mean, this function is basically a function from x to s. H of g of f is what? The domain of this function is x. The codomain of this function is h codomain. So basically your function h of g of f is a function from set x to set s. So that is true for every x. So any element that you take small x, that comes from the domain set, obviously. Now RHS, right hand side. Again your h of g of f. Again this is a function from the set x to set s, because the domain of f will be the domain of this function, which is x, to the codomain of h, the last function is h. You have to read the function like this, because first f is applied, then g is applied, then h is applied. Now what is the definition of this function? H of g of f, h of g of f of x is equal to h of g of f of x. Right? So this function h of g is operating on f of x first. Then this becomes h of, now g is going to be operated on this f of x. So it becomes h of g of f of x. Probably I'll write it in the same line. It doesn't matter. I'm writing it here because that's how I wrote this. That is equal to h of g of f of x. Right? Now this is true for every x belonging to x. Now both h of g of f of x is also h of g of f of x. H of g of f of x is also h of g of f of x. So both are same. So therefore we can say h of g of f is equal to h of g of f. So both this function and this function are equal. So we can say that composition of function is associative. Composition of functions is associative, which means it satisfies associative law. Composition of functions is associative, right? So that's the proof for this. So both h of g of f is also h of g of f of x. H of g of f is also h of g of f of x. So both are same, therefore these two are same. So now we write only take the function equal to function, because this function of x is equal to this function of x for every x in x. Therefore these two are equal functions. Both are one and the same function. They are equal function. Right? Now let's go to the next one, which is example 27. So let me erase this side. Hope all of you have taken the notes. All of you can pause the video, take the notes. I'm erasing this. So now next one is example 27. Example 27. So what is given is, consider the function. So f is a function from, so f is a function. So given is f is a function from the set 1, 2, 3, 1, 2, 3 to the set a, b, c. And then g is another function, g is another function from the set a, b, c to the set apple, bat and cat. Apple, bat, cat. Fine. Now, what we should do also, it is defined. So, f is defined as f of 1 is equal to a, f of 2 is equal to b, f of 3 is equal to c. Again, g of a is defined as g of a is equal to apple, g of b is equal to bat, comma, g of c is equal to cat. That is how it is defined. Say f is defined like this, g is defined like this. Now, what we have to prove or show is that. So to prove is we have to show that f of g are invertible. So we should show f, g and g of f are invertible, which means we have to show that these are invertible functions, f, g and g of f. That is first part. First we have to show that they are invertible. Second is we have to find them. We have to find f inverse, g inverse and g of f the whole inverse. We have to find the inverse of these three. And the third one that we have to prove is we have to show that g of f inverse is equal to f inverse of g inverse. F inverse of g inverse. This also we have to prove. Right? So the question may look confusing or like proving many things, but all are easy proofs. So let's go step by step. So proof. Let's prove that f, g of f are invertible first. Now f of 1 is a, f of 2 is b, f of 3 is c. So clearly every element, 1 goes to a, 2 goes to b, 3 goes to c. That is the definition of this. So we'll say clearly f is 1-to-1 and onto function. Right? It's a 1-to-1 because one element goes to one image, another element goes to another image, third element goes to another image. So clearly f is 1-to-1 and onto because every element here has a pre-image. Right? So a pre-image is 1, b pre-image is 2, c's pre-image is 3. So clearly f is 1-to-1 and onto. Right? Therefore, we can say f is invertible. A function which is 1-to-1 and onto. A function which is 1-to-1 and onto is called as an invertible function. So we can say it is invertible. F is invertible. So similarly, we can say clearly g is 1-to-1 and onto. Therefore, onto means onto function. Therefore, g is invertible. The function g is also an invertible function because g is also 1-to-1 because a goes to apple, here b goes to bat, c goes to cat. So it is 1-to-1 because no two different images, no two different elements have the same image. And it's not like a and b both are going to single apple or single bat. Right? So similarly, it is onto because every element here, for apple, a is the pre-image. For bat, b is the pre-image. For cat, c is the pre-image. So every element here, we are able to find an element here such that g of c gives me cat. If I take any element bat, then I am able to find an element b in this set such that g of b is bat. Therefore, it is onto. So since g is 1-to-1 and onto, g is invertible. So a function which is 1-to-1 and onto, a function which is 1-to-1 and onto, which is called as bijective, then we can say immediately that is invertible, which means we can find the inverse of the function. Now the third one is we have to prove that g of f is invertible. To prove g of f is invertible, we have to prove that g of f is 1-to-1 and onto. Now again we have a theorem which we proved earlier. That is, it says since f and g are 1-to-1 function, then g of f is 1-to-1. Sorry, 1-to-1. G of f is 1-to-1. So we have proved that g of f is a 1-to-1 function. Also, since f and g are onto function, then g of f is also an onto function. the composition of f and g, that will also become onto function. This is one more theorem. These two theorems we studied in our example. If you look at example 18, is this, which says if f and g are 1 to 1, then g of f is 1 to 1. And example 19 says that if f and g are onto, then g of f is onto. Right? So this is example 18 and example 19. You can refer in your book, which we did it in the which I did it in the previous videos. So now since f and g are 1 to 1, g of now g of f is 1 to 1 and g of f is onto. So what we got now? Therefore, g of f is 1 to 1 and onto. So g of f is invertible. So now we have proved that f is invertible, we have proved g is invertible, and also we proved g of f is invertible. So the first part is done. Now we have to find the inverse of f inverse, g inverse, and g of f inverse. We have to find the inverse function of this. Now second part. So this is the first part. Right? Proof for the second part is we have to find f inverse, g inverse, and g of f inverse. Now again f inverse, let's define f inverse. We can define like this. So let's define f inverse as, now we are going to define the f inverse, right? So f inverse is a function. Let's define f inverse as it's a function from this set to this set. If f is a function from this to this, then we can define a function f inverse from this to this. So that will be from the set A, B, C to the set 1, 2, 3, and the definition is going to be, we are going to define now f inverse of A. F inverse of A will be, this is we are defining f inverse of A is going to be, now in the f inverse of A we will define it as 1, the reverse of this, so 1. Then f inverse of B will define it as 2. Then f inverse of C will define it as 3. Now we should show that this function is inverse of f. Just because if we put f inverse, it doesn't mean that it is inverse of f. We have to prove that f inverse f minus 1, f inverse is the inverse of f. Now how do we prove that? So we'll have to do, now we'll have to do what is, we have to show that, so to show that one function is the inverse of other function, we have to take the composition of the functions in both the ways. So suppose if I want to show that g is the inverse of f, right, then I have to show that g of f and f of g are giving you the identity function, right? So which means let's try to find the composition of f and f inverse. So now what is f of f inverse? We will show that this is equal to x. If we show the f of f inverse is equal to x and f inverse of f is also x, then f inverse is the inverse of f. Now, so this is of x. We'll define this function. Now f of f inverse. So this is a function from which set to which set? F inverse. F inverse starts from which set? ABC. So this is a set from ABC. This is a set from ABC to ABC. Right? This is a set from ABC. The domain of F1. F1 starts from this, and F ending with what? F is ending with ABC. So it's a set from this ABC to this ABC. That is f of f inverse function. And let's define that as f of f inverse. Let's find that. What is f of f inverse of this element A? This element A goes to which set? So that is equal to f of f inverse of A. That is equal to f of, what is f inverse of A? F inverse of A is 1. That is f of 1. And what is f of 1? F of 1 is A. So A. So which means A is getting mapped to A. A goes to A. Similarly, f of f inverse of B will be equal to f of f inverse of B. That is equal to f of, what is f inverse of B? F inverse of B is 2. So f of 2. And what is f of 2? F of 2 is B. So B. So B is going to be. Similarly, f of f inverse of C will be f of f inverse of C, and f inverse of C is 3. So you get f of 3. F of 3 is C. So C goes to 3. C. So therefore what we have got? Every element is going to itself. So we can say our f of f inverse is equal to identity function. F of f inverse is identity on this set ABC. So we put like this: I of A comma B comma C. I in the bottom we'll write ABC, which means it's an identity function from this set I. It's an identity function from set ABC to set ABC. That is f of f inverse. Now similarly, we need to find what is f inverse of f. right? So what is f inverse of f? So f inverse of f function, it is from which set to which set? F inverse of f is a function from f is a function from which set? Now we have to do the reverse. F inverse of f. So f is a function from 1 to 3. So it will be from 1 to 3 to f inverse ends with which function? F inverse ends with 1 to 3. So it is 1 to 3 to 1 to 3. Right? And let's try to find where each element is getting mapped to. So 1 goes to where, 2 goes to where, we have to find. And obviously we should prove that 1 goes to 1, 2 goes to 2, 3 goes to 3. So that it also becomes an identity function. So now what we have is now here. Now f inverse of f of, let's take the first element 1. 1 is getting mapped to which element here? 1. That is 1. That is equal to f inverse of f of 1. And what is f of 1? F inverse of f of 1 is a. So f inverse of a. And what is f inverse of a? Is 1 as per the definition here. So this is the definition that we are defined. And it is easy to define. If you want to define the inverse, you have to reverse this. F inverse of a will be equal to 1. F inverse of b will be equal to 2. F inverse of c will be equal to 3. So that is equal to 1. And f inverse of f of 2 will be equal to f inverse of f of 2. That will be equal to f inverse of f of 2 is b, and if f inverse of b is 2. So 2 goes to 2. Similarly, f inverse of f of 3 equal to f inverse of f of 3. That is equal to f inverse of c. That is equal to 3. Because f of 3 is c. So f inverse of c is 3. So 3 goes to 3. Therefore, what we have proved? We have proved f inverse of f is also identity function. Because every element goes to every other element means it becomes identity. F inverse of f is an identity function on which set? It's coming from the set 1, 2, 3 to 1, 2, 3. So I'll put 1, 2, 3. So this is your f of f. Therefore, we can say therefore f inverse is the inverse of the function f, which is this function. We proved that because we showed f inverse of f is also I, and f inverse of f inverse is also I. F inverse of f is also I. Therefore, this is the inverse of f. Fine. Now let's go to the next one, which is we have proved this one. Now we need to prove G inverse. Same way, we are defining the inverse of G in the similar way. So what do we do there? Again, we'll have to define G inverse. So let's define the another function G inverse as, it will be from which set? It will be from the reverse set. Apple, bat, cat. So it will be from apple, bat, comma, cat to the reverse. G inverse will be reverse, ABC. To the set ABC, and we are going to define. So G inverse of apple, we are going to define it as A. G inverse operating on this element, we are mapping it to A, because we'll just write the reverse of this for inverse. Comma, G inverse of bat equal to B, comma, G inverse of cat equal to C. Fine. Now we need to show that this G inverse is the inverse of G. Is the inverse of this function G. Now to do that, we have to do the similar thing. We have to define you have to find what is G of G inverse. So what is G of G inverse? Now G of G inverse, it's a function from which set to which set. We have to prove that G of G inverse is equal to I. And again, G inverse of G is also I. Once you prove that G of G inverse is I and G inverse of G is I, then G inverse becomes the inverse of G. Right? Now what is G inverse? Starts from which set? G inverse is starting from apple, bat, cat. So this will be from apple, bat, cat to the set where is G ending. Ending set is this, which is codomain. It's also apple, bat, cat. Now let's find what is G of G inverse of apple. G of G inverse of apple will be equal to G of G inverse of apple. That will be what is G inverse of apple? G inverse of apple is A. So G of A. Again, what is G of A? G of A is apple. right? Now G of G inverse of bat. So apple is going to apple. We should prove that bat is also going to bat. So G of G inverse of bat. And G inverse of bat is B. G inverse of bat is B. So it becomes B. G inverse of bat becomes B. So G of B is again bat. Because G of B is bat. Similarly, G of G inverse of cat is equal to G of G inverse of cat. That is equal to G of G inverse of cat is C. C of G is again cat. Now apple goes to apple, bat is going to bat, cat is going to cat means what? Your G of G inverse is nothing but an identity function. I function on the set AB apple, bat, cat. So here I'll write apple, comma bat, comma cat. Very small, we'll write the set below the I in the suffix of I. So now G of G inverse is I. Now similarly we should find the reverse. What is G inverse of G? And that is a set from which set to which set? That's a function from which set? Which set to which set? Now G inverse of G. It's a function from. Now let's take the set G is starting from A, B, C. So it is starting from A, comma B, comma C. 2, it is ending with G inverse. G inverse is ending with which set? A, B, C. A, B, C. So we have to write the starting set of G here and the ending set of G inverse. So starting set is domain, ending set is codomain. So it is from ABC to ABC. Now let's define what is G inverse of G. G inverse of G of the first element A. So that is G inverse of G of A. And G of A is apple. So G inverse of apple is A. G inverse of apple is A. So similarly, G inverse of G of B equal to G inverse of G of B. That is G inverse of G of B is bat and G inverse of bat is B. Similarly, G inverse of G of C equal to G inverse of G of C. That is equal to G inverse of cat and G inverse of cat is C. So your A goes to A, B goes to B, C goes to C. Therefore, G inverse of G is also an identity function on which set? Small this ABC set. A, comma B, comma C set. So we have proved G of G inverse is also I. G inverse of G is also I. Therefore, we can say G inverse is the inverse of G function. G inverse is the inverse of G function. Which is, so we have found this and this. So we have proved this part, we have proved this part, we have proved this part. Friends, we have to prove the rest of the things, but we are running out of space on the board. So all of you can pause the video and take the notes. I will continue the next part, which is G of F of inverse. So I'm erasing few of them. Here I'm continuing here. I'm keeping the question as it is. So the continuation of this question, so I'll say continuation, continued. The continuation of this. After this, I'm writing this. Right, because we have to prove this. So we have done till this here. That is, which is this is done, this is done. Now we have to do this. We have to find G of F inverse. So before we find G of F inverse, let's find what is G of F. Only then we can find G of F inverse. Now what is G of F? The G of F function we should find. And G of F is a function from which set to which set? It's from the starting set of F 1, 2, 3 to G's codomain, that is apple, bat, cat. Now what is the definition? So now we have to define G of F. What is G of F? See, here we need to know what is G of F. Only then we can talk about the inverse of G of F. So here we know F definition is given, G definition is given. So we could find F inverse and G inverse. Now here before we find G of F inverse, we should find what is G of F function, right? So what is G of F function? And it is a function from set 1, 2, 3 to apple, bat, cat. So G of F function is different. We have to, for each element we have to find where it is going. So G of F of 1 is equal to G of F of 1. That is equal to G of, what is F of 1? F of 1 is A, G of A. And what is G of A? G of A is apple. So 1 is getting mapped to apple. Now similarly G of F of 2 is G of F of 2. That is equal to G of, what is F of 2? F of 2 is B. So G of B, and G of B goes to bat, BAT, bat. Next one is G of F of 3. That is equal to G of F of 3. and f of 3 is g of f of 3 is c, and g of c is cat. So we have defined the function g of f. Now once we define the function g of f, now we can find the inverse of g of f. Now what will be the inverse of g of f? Let's define the inverse of g of f. So g of f inverse function, it's also a function. I'm going to define that function. How do you define that function? We have defined the set first. Now g of f is a function from this set to this set, means the inverse g of f inverse function, which we need to prove that the function that we are going to define now here is going to be the inverse of this function. So that will be defined in the reversed way. If g of f is from this to this, the g of f inverse will be from this set to this set, which is from apple, bat, cat to the set 1, 2, 3. And how do we define that? Now the definition of g of f inverse, right? G of f whole inverse, we can't write this as g of f of inverse nor anything. So we need to find that. So we are going to define this. Now g of f of, so we got the function g of f. From this we can define the inverse. Like how we will define the reverse of this. So 1 is going to happen. So this is g of f of, we'll take it as apple. G of f inverse of apple is equal to, we'll put apple is equal to 1. We'll define like that. We are defining here. We are not trying to show that g of f inverse of apple is equal to g of, we can't write like that because we can't separate. The whole inverse is this. So we are going to define each element here is getting mapped to which element. So that I will try to do the reverse of this. So apple will go to 1 because g of f is 1 is going to apple. Inverse means we have to define the inverse in the reverse way. Apple is going to 1. Then comma and g of f whole inverse of next element is bat. We are going to define it as 2. Bat is 2 goes to bat, so bat will go to 2 in the inverse. Comma g of f the whole inverse of cat will go to 3. So like that we have defined now g of f inverse. Now we should show that g of f inverse is the inverse of this function. So we have defined this like this. How we defined g here? G inverse. Like that we have defined this. Now to prove that this is the inverse of this function, to prove this is an inverse of this, right? We have to prove that. So next is we have to find g of f the whole inverse. And we should prove that it is equal to I. Like how we proved that g of g inverse. Instead of g, we are putting the entire set. This set of its inverse set, another function, this function of another function's inverse. Just because I say g of f of inverse, it doesn't mean that g of f of inverse is the inverse of this. You have to prove that it's an inverse. For that, you have to take the composition of that function and which we are trying to prove it as an inverse. You have to take the composition of these two and show that the composition is a identity function. So we have to prove that this is equal to identity function. So this is equal to, and this will be a function from which set to which set? G of f of inverse. This starts from which set? Apple, bat, cat. So apple, bat, cat. First is the definition of the set. Then we will define the function. Now, what is the ending set of g of f? G of f. G of f is ending with apple, bat. This is also apple, bat, comma cat. Fine. Now let's try to find for each element where it is going. Now let's try to get g of f inverse of the first element apple. That will be equal to g of f inverse of apple. That is equal to, what is g of f inverse of apple? G of f inverse of apple is 1. So that will become g of f of 1. And what is g of f of 1? G of f of 1 is apple. That is equal to apple. So which means apple goes to apple. Similarly, g of f inverse of the second element. Second element is bat. Bat is equal to g of f whole inverse of bat. that is equal to g of f inverse of bat is what? G of f inverse of bat is 2. So g of f of 2. And what is g of f of 2? Is bat. Now g of f whole inverse of cat is equal to g of f inverse of cat, that is equal to g of f of 3, because g of f inverse of cat is defined as 3 and g of f of 3 is cat. So what we have got? We got apple goes to apple, bat goes to bat, cat goes to cat, means our g of f the whole inverse is equal to identity function. And identity function on what? Whenever every element goes to the same element, bat goes to bat, cat goes to cat, then we can say this function is equal to I function. On which set? It sets on apple, bat, cat. So we'll write apple, bat, cat. Close. Now we have to do the reverse also. So clear? Now we should do the reverse of the composition, which is we have to find now this one, g of f inverse of g of f, and it is a function from which set to which set. Now what is starting of g of f? G of f starts from which set? G of f is here 1, 2, 3. 1, 2, 3. 2 g of f the whole inverse ends with g of f the whole inverse set ends with this set 1, 2, 3. So it is from 1, 2, 3 to 1, 2, 3. 1, 2, 3 to 1, 2, 3. Fine. It's a lengthy one, but we'll do it. I mean, it's the same repetition that we are doing. That's it. Like how we define the inverse, and we have to prove that the function and the one which we claim as an inverse, the composition should give you I on either side, whether f of f inverse or f inverse of f. Similarly, g of f inverse or g of f inverse of g of f. Now what is this? G of f inverse of g of f of is going to operate in the first element 1. That will become g of f inverse of g of f of 1. And what is g of f of 1? G of f of 1 is apple. So you get g of f inverse of apple. And what is g of f inverse of apple? G of f inverse of apple is 1. So 1 goes to 1. Similarly, g of f inverse of g of f of 2. The element 2, next element is 2. Is g of f inverse of g of f of 2. That is equal to g of f inverse of, what is g of f of 2? G of f of 2 is bat. So bat. And bat goes to 2. So g of f inverse of bat. G of f inverse of bat is 2. G of f inverse of bat is 2. Similarly, g of f inverse of g of f of 3. That is equal to g of f inverse of g of f of 3. That is equal to g of f inverse whole inverse of g of f of 3. G of f of 3 is cat. So you get cat. And g of f of whole inverse is 3. Right? G of f whole inverse of cat is 3. So this whole value is 3. So now what we got? 1 goes to 1, 2 goes to 2, 3 goes to 3. Therefore, g of f of inverse of g of f of it is an identity function on the set 1, 2, 3 on this set. So we have proved now g of f the whole inverse is also I. G of f the whole inverse of g of f is also I. Therefore, we can say g of f the whole inverse is the inverse of g of f function. So just because we call this a g of f of whole inverse, it doesn't make it as an inverse of this function. We are proving that inverse. To prove that inverse, we have to do this. This into this should be identity function, not into composition of g inverse of f the whole inverse into g of f is also an identity function. Only then the one that we defined here, it becomes the inverse of this function. Now we have proved, so we have done this part also now. The last part is that we have to show that g of f inverse equal to f inverse of G inverse. Now, which means we should find what is F inverse, what is G inverse. We have to take the composition of these two. Right? The third part is we should show that. No, we know what is G of F inverse. We know G of F inverse is this function. G of F inverse is this function. This to this. So this is your G of F inverse. It is from which set to which set, and what is the definition. Now we will find what is F inverse of G inverse. F inverse of G inverse also should be the same thing. Apple should go to 1, bat should go to 2, cat should go to 3. If you get that, then we can say G of F whole inverse and F inverse of G inverse both are same. Now let's try to find what is F inverse of G inverse. So now this F inverse of G inverse, and it's a function from which set to which set. Now G inverse is function from which set? Which I erased it. So G inverse is a function from this set to this set. So G inverse is the domain of G inverse is this set, which is the codomain of G is the domain of G inverse. So which is apple, bat, cat. 2, right? Now 2, the function which is F inverse. F inverse, what is the ending function of F inverse? The ending function of F inverse is starting function of F. The domain of F is the codomain of, that is 1, 2, 3. Now if you see that this one, G of F inverse, which is this, that is also from the same set to same set. Even F inverse of G inverse is also from apple, bat, cat to 1, 2, 3. So the sets are matching. Now we should show the definition is also matching, which means we should find what is F inverse of G inverse. So we have to find what is F inverse of G inverse of this element, apple. Right? Here we have got G of F inverse of apple. It is going to 1. We have to prove that that is also 1. If this also becomes 1, then similarly bat should go to 2 and cat should go to 3 for this function also. Then we can say this function and this function are equal. Therefore, these two will become equal. Clear? Fine. Now let's go and do that. So what do we have next is F inverse of G inverse of apple, that is equal to F inverse of G inverse of apple. That is equal to F inverse of, not what is G inverse of apple. G inverse of apple will be the G inverse which I had erased, but the inverse that we got or which we defined was the reverse of this, which is A. G inverse of apple is A. So G inverse of apple is A. And what is F inverse of A? F inverse of A is the reverse of this. F inverse of A is 1. That's how we define our F inverse and G inverse, which if you see the previous notes that you had taken, where we defined F inverse and G inverse. There if you see, you will get this. Now what is F inverse of A? 1. Therefore, apple goes to 1. So here also apple was going to 1. Right? Now again F inverse of G inverse of bat. That is equal to F inverse of G inverse of bat. That is equal to F inverse of, what is G inverse of bat? G inverse of bat is, G inverse of bat goes to B, which is F inverse of B, and F inverse of B goes to 2. 2. Therefore, your bat goes to 2, there also bat goes to 2, here also bat goes to 2. So they are matching. Even if for cat goes to 3, then it will match for all the elements. Therefore, you can say this set, this function and this function and this function are equal. So the last element, F inverse. This is F inverse of G inverse of cat. That is equal to F inverse of G of cat. G inverse of. That is equal to F inverse of, what is G inverse of cat? That is C. And what is F inverse of C? That is 3. Right? So cat goes to 3. Now all apple goes to 1. Apple here goes to 1. Here also apple goes to 1. Then bat goes to 2. Here also bat goes to 2. Cat goes to 3. Cat goes to 3. Therefore, every element, the images are matching. Therefore, these two are equal functions. Therefore, we can say like this. We can say that G of F inverse of X is equal to F inverse of G inverse of X for every X belonging to the set apple, bat, cat. Apple, bat and cat. For every X belong to this set, your G inverse of F of X is same as F inverse of G of X. Which means this function of X is any element, is same as F inverse of G of X. So for every element it is same. If I put x as apple, then g of f inverse of apple will give me 1, and f inverse of g inverse of apple is also 1. Similarly, if I put bat, we will get 2 here, this will also be 2. For cat, cat goes to 3 as per this, cat goes to 3, and as per this, cat goes to 3. So every element is same, therefore they are equal functions. Therefore, we can say g of f the whole inverse is equal to f inverse of g inverse. So we have proved this. Clear? Fine. So all of you can pause this video and take the notes. In this continuation, we proved till this in the previous section, and then I erased. After erasing, we continued from this, and the proof for this starts from here. The continuation of the previous continuation of the previous one. That comes continuation of this. Fine. So all of you can pause the video and take the notes. I will go to the next one. Next problem is Theorem 2. So I'll erase this. Now Theorem 2 in page number 17. Page number 17, Theorem 2. So what the Theorem 2 says is, if f is a function from x to y, and then g is a function from set y to set z, are invertible, two invertible functions. Two invertible functions, which means the inverse exists for them. Then g of f is also invertible. We should show that. So to prove this is given. Given as f is a function from x to y set, f is a function from set x to set y, g is a function from set y to set z, two invertible function. To prove is, what we have to prove? We have to prove that g of f is also invertible, which means g of first part that we have to prove is g of f is invertible. Then second is, we have to prove that also in general g of f of whole inverse equal to f inverse of g inverse. So here we proved the similar result, but this we proved for a particular function. This is in general. It is generally we are proving. Here we proved for apple, bat, cat, 1, 2, 3 and all that. For a particular set we proved. It is for any set x to y and g is from y to z. Then for any two sets this is true. If f and g are two invertible functions, then g of f is also invertible, and the inverse of g of f will be equal to f inverse composition g inverse. F inverse of g inverse. We have to prove these two. This is, we are proving for any general. So proof. Any set x, y, z, it is true. And for any function f. So proof is, now we have to prove first is g of f is invertible. For that f and g are invertible. Say so f is invertible. So f is 1 to 1. F is 1 to 1 and onto. Because if f is an invertible function, then you can say f is 1 to 1 and onto. If f is 1 to 1 and onto, you can say that f is an invertible function. The converse is also true. Similarly, g is invertible, that is given in the question. If g is invertible, so g is 1 to 1 and onto. And onto. So what we got? We got f and g are 1 to 1. So we'll say f comma g are 1 to 1. So by our example 18 in your textbook, if f and g are 1 to 1, that is also called that can also be called as a theorem. If f and g are 1 to 1, f and g are 1 to 1, so your g of f is also 1 to 1. And f and g are onto function. So g of f is also onto. Now what we have proved? We have proved g of f is 1 to 1, g of f is onto. If g of f is 1 to 1 and onto, then we can say g of f is invertible. Now we will say since g of f is 1 to 1 and onto, right? Therefore, g of f is invertible. We have proved that it's an invertible. So this part is done. We cannot find the inverse now. We are saying that the inverse exists. It's not like all the functions will have inverses. But if the function is 1 to 1 and on to, it will definitely have inverse. It will definitely have an inverse. That's why that when a function has an inverse, we call the function as an invertible function. Fine. Okay. Now next what we have is, so this part is done. We have to prove now g of f of whole inverse equal to f inverse of g inverse. So to prove that g of f is an inverse, g of f whole inverse of this is equal to f inverse g inverse, we will try to take the composition of these two, which means let's try to find this. So we have to prove that f inverse of g inverse is the inverse of g of f. F inverse of g inverse is inverse of g of f function. So to prove that this is an inverse of g of f function, we have to take the composition of g of f with this function and prove that it is an identity function, and f inverse of g inverse composition g of f, not g of f inverse, g of f, that also should give you identity function. So let's try to find this. Now let's find g of f inverse of g inverse. We are going to find this. Now suppose if this becomes I, we will do the reverse. That is also I means we can say f inverse of g inverse is the inverse of this function g of f, which means f inverse of g inverse will become g of f of whole inverse. We will get this. So which is equal to, now this is equal to now g of f inverse of, see we can associate like this, of g inverse. We can associate because the associative law is true for composition of functions. So it is like this. So I can associate this and this. So now that is equal to g of, now f of f inverse. F of f inverse is an identity function I function. So f of f inverse. So if you take the composition of f and f inverse, you will get identity function because f inverse is the inverse of f. F inverse is the inverse of f. So g of I of g inverse. Now g of I, if a function g with the composition of I function, which is an identity function, will give you back the same g function. So this g of I will be same as g. G of this is g inverse. And g composition of g inverse will again give you the identity function I. So what we have proved? We have proved g of f inverse of g inverse is equal to I. Fine. Now we will try to prove the reverse. The reverse case, which means f inverse of g inverse with g of f. If this also should become I, this also gives you I, then we can say that the f inverse of g inverse is the inverse of g of f. So what is this? That will be equal to f inverse of g inverse of, so this is of g. I am going to associate these two because associative law is true for composition of function. Fine. Now that is equal to f of g inverse of g is I function of f. Now here we can associate anything. We can associate these two also. That is equal to f inverse of I of f. Identity function applied on the function f will give you the same function f. So f of f inverse of f. So because this will become f. Now f inverse of f is again I. So we got f inverse of g inverse of f of g. That is also becoming I. Sorry, g of f. Of g of f becomes I. So this is also I. This is also I. Which means this function is the inverse of this. So therefore we can say g of f. We can say therefore we can say f inverse of g inverse is the inverse of the function g of f, which means f inverse of g inverse is equal to g of f the whole inverse. The inverse of g of f from g of f whole inverse. So we have proved this. Fine. So this is true for any two functions g and f. This is always true. If you want to find the g of f the whole inverse, it is nothing but f inverse composition of G inverse. F inverse of G inverse. Fine, so all of you can pause the video and take the notes. I will go to the next problem, which is example 28. Let me erase this section, this side. Okay, so the next question is example 28. Right, so what it is, it says S is equal to 1, 2, 3. So what is given? So given is set S is 1, 2, 3, 1, 2, 3. Is a set. Determine whether the function given by F is a function from S to S, we defined as below, have inverses. Check whether. So what you have to say that check if the function F from S to S defined below right, check if functions defined below have inverses. Find F inverse if it exists. We have to find the F inverse if it exists. So we have to, which means there is a function given. So it has three parts. So A question is the function is defined as 1, 1, 2, 2, 3, 3. 1, 1, 2, 2, 3, 3. Now we should check whether this function has inverse. F has an inverse. If it has an inverse, then we have to find what is F inverse. So now for a function to have inverse, the function should be 1 to 1 and not 2. If the function is 1 to 1 and not 2, then we can say that the function is invertible, which means the function has the inverse. So we'll say from the definition, see 1 is going to 1, 2 is going to 2, 3 is going to 3. So it's a 1 to 1 function. And also it is on to, right, because it is from 1 to 3 to 1 to 3, S to S. So we'll say clearly F is 1 to 1 and on to. Why 1 to 1? So 1 goes to 1, 2 goes to 2, 3 goes to 3. So it's like not like two elements are going to the same element. Two distinct elements have two distinct images. Or distinct elements of S domain has or have distinct elements as their images. So F is 1 to 1 and on to. So therefore F is invertible. So we have proved first is F is invertible because F is 1 to 1 and on to. And it is on to because every element here has an element here. If I take an element 3, which is getting mapped to 3, 3 is getting mapped to 3. If I take an element 2, this 2, the element here is 2, that maps to 2. So the element 1, the 1 here maps to 1. So every element here has an element here, says that F of the element X is equal to the element in the codomain. Right? So therefore F is invertible. Now if it is invertible, we have to find F inverse. So F inverse again we can define. So F inverse we have defined it as, F inverse. So find F inverse. So F inverse we have to, it's a set from, again, if F is from S to S, F inverse from the reverse. So this S to this S, but both are same. It is also from S to S. And F inverse is defined as, F inverse we'll define it as, we can define it in this. See, what is the meaning of 1, 1 goes to 1, 2 goes to. The meaning of this is actually F of 1 is 1, F of 2 is 2, F of 3 is 3. That is the meaning of this. That is the meaning of F of 1, 1 is, F of 1 is 1, F of 2 is 2, F of 3 is 3. That is the meaning of that. Right? It's not going to, this implies, I'll put it as implies. This means this. So which means F inverse will be, F inverse we will define it as the reverse of this. So 1, 1, 1, again 2, 2, the reverse of 2, 2 is 2, 2, the reverse of this is 3, 3. So what is the meaning of this? Again 1 goes to 1, 2 goes to 2, 3 goes to 3. Right? Close. Fine. So this is your F inverse. We can show that clearly. We can even show that F inverse of F gives you identity function. See, this is already an identity function. So we can also show that F inverse of F is equal to I. So we can, which we have showed in the earlier example, we will say we can, so clearly, or we'll also say that, or I can prove also, we can try to prove, we'll have to prove that both the ways, right? It is so obvious that it is, one is the inverse of this. If you define like this, then it becomes the inverse of this. But, we can even show that this is an inverse, because if it exists, we have to show that if this is an inverse of this. So we'll find what is F of F inverse. We have to show that it is I. What is F of F inverse? F of F inverse is a function from which set to which set? F inverse again from S to S. Right? And what is F of F inverse of 1? That is equal to F of F inverse of 1. That is equal to F of 1. That is equal to 1. Because F inverse of 1 is 1. Right? So, and F of 1 means F of 1 is also 1. So, meaning of this is what? Meaning of this is F inverse of 1 is 1. F inverse of 2 is 2. That is meaning of this. And F inverse of 3 is 3. Hope I am not hiding. F inverse of 2 is 2, comma, F inverse of 3 equal to 3. Fine. Now F of F inverse of 1 equal to F of 1, which is 1. Then F of F inverse of 2, that is equal to F of F inverse of 2, that is equal to F of 2, that is equal to 2. Similarly, F of F inverse of 3 equal to F of F inverse of 3, that is equal to F of 3, that is equal to 3. Because F inverse goes to 2 and F of 2 is also 2. So therefore, what we have shown? We have showed F of F inverse equal to I function. I on the set S. So we can put IS. So similarly, we can show that we can show the reverse. So F inverse of F from the set S to S. Again, it will be from, here it is only one set, S to S. So everything will be from S to S. So F inverse of F. F inverse of F means F inverse of F of 1. The element 1 from this set S. That will be F inverse of F of 1. That will be F inverse of 1. That will be 1. Now F inverse of F of 2 will be equal to F inverse of F of 2. That will be equal to F inverse of F of 2. F of 2 is 2. And F inverse of 2 is 2. Similarly, F inverse of F of 3 equal to F inverse of F of 3. That is equal to F inverse of, what is F of 3? Is 3. Is equal to 3. So therefore, what we have got? Therefore, we have got F of F inverse of house. That is equal to I function. I on the set S. So F inverse of F. F inverse of F. F inverse of F is also I. F of F inverse is also I. Therefore, F inverse is the inverse of F. Fine. So F inverse is the inverse of F, because we have proved that F of F inverse is also I. F inverse of F is also I. Right. So this is for A. Now for the B part, I'll erase this. So the B part is, B is, F is defined as 1, 2, 2, 1, 3, 1. Now what is the meaning of this? Which means F of 1 is 2, F of 2 is 1, F of 2 is 1, then F of 3 is 1. F of 3 is 1. Now is F is, first we have to check whether F is 1 to 1, and then we have to check whether F is on to. Now clearly F is not 1 to 1, because F of 2 also goes to 1, F of 3 also goes to 1. So we'll say F is not 1 to 1, because F of 2 equal to F of 3. both are equal to 1, but 2 is not equal to 3. The two different images, they have the same, two different elements have the same image. When two different elements have the same image, then it's not a one-to-one function. F is not one-to-one because f of 2 equal to f of 3 equal to 1. So therefore, f is not invertible. Because the moment f is not one-to-one, then we cannot find the inverse. So f is not invertible. So we need not find the inverse, because we need to find the inverse only if it exists. Right? So this ends the second B part. Now the C problem. See what it says. C is again, f is a function which is from, so the function f is 1 comma 3, sorry, in the bracket I have to put 1 comma 3 comma 3 comma 2 comma 2 comma 1. So what is the meaning of this? The meaning of this means our f is defined as f of 1 is 3, that is the meaning of this, and f of 3 is 2 comma f of 2 is 1. F of 2 is 1. That is the meaning of this. If they give like this, which means 1 is getting mapped to 3, 3 is getting mapped to 2, 2 is getting mapped to 1. Now we'll check if it is 1 to 1. Yes, clearly it is 1 to 1 because 1 is going to 3, 3 is going to 2, 2 is going to 1. Right? Suppose if you put the arrow diagram, you can easily make that out. So this is 1, 2, 3. This is your function f. This is set s, set s. Now 1 is going to where 3. So here also put 1, 2, 3. Now 1 is going to 3. Then 3 is going to 1. 3 is going to 2. Then 2 is going to 1. So clearly this function is what? 1 to 1 and on to. Right? So we'll say clearly same like this. Clearly f is 1 to 1 and on to. So therefore f is invertible. Which means we can find the inverse of f. Now how do we define the inverse of f? So f inverse is defined as, it is also from the set S to S. Right? Now f inverse will be defined as, so f inverse will be equal to 3 comma 1. We have to reverse this. 3 comma 1. Then 2 comma 3. 2 comma 3. 1 comma 2. 1 comma 2. That is how you define the inverse. What is the meaning of this? Meaning of this is f inverse of 3 is 1. F inverse of 2 is 3. F inverse of 1 is 2. That is the meaning of this. Fine. Now we need to prove that this f inverse is the inverse of this function. So for that we have to find what is f of f inverse. Now f of f inverse is a function from which set to which set. F inverse starts from where S. So it is from S to S. So now what is f of f inverse of an element 1 from this set? That is equal to f of f inverse of 1. That is equal to f of, what is f inverse of 1? F inverse of 1 is 2. So f of 2. And what is f of 2? F of 2 is 1. So 1. So 1 goes to 1. Similarly, f of f inverse of 2 is equal to f of f inverse of 2. That is equal to f of f inverse of 2 is 3. So f of 3 and f of 3 is sorry here. F of 3 is 2. This is previous sum. F of 3 is 2. So 2 also goes to 2. Similarly, f of f inverse of 3 is equal to f of f inverse of 3. That is equal to f of, what is f inverse of 3? F inverse of 3 goes to 1. And what is f of 1? F of 1 goes to 3. So 1 goes to 1, 2 goes to 2, 3 goes to 3 means our f of f inverse is an identity function on S, on the set S. So similarly, we find the reverse. F of f inverse of f of 1. The reverse. I am writing it here itself to fit it in this board. So the continuation after this, I am writing this. The f of f inverse of 1 is equal to f inverse of f of 1. That is equal to what is f inverse of f of 1. What is f of 1? F of 1 is 3. And f inverse of 3 is 1. So similarly, f inverse of, and again f inverse of f is a function from S to S. So f inverse of f of 2, second element is 2. Each element here we should find the image. So f inverse of f of 2, that is equal to f inverse of, what is f of 2? F of 2 is 1. And what is f inverse of 1? F inverse of 1 is 2. Now f inverse of f of 3 equal to f inverse of f of 3, that is equal to f inverse of f of 3. F of 3 is 1. F of 1, and what is f of 1? F of 1 is 3. So 1 goes to 1, 2 goes to 2, 3 goes to 3. Therefore, we can say f inverse of f is also identity function on set S, IS. This S denotes this set S. So therefore, we got this and both are I. Therefore, the final conclusion is f inverse is the inverse of f. Inverse of f. Just because we write f inverse, it doesn't mean that this function is the inverse of this function. You have to prove that f of f inverse and f inverse of f both are getting the identity function. Only then we can say that f inverse is the inverse of f. So we have found the inverse for f also. Okay. So this completes your example 28. All of you can pause the video and take the notes. I will stop the session here. You can watch my next session for the continuation of this. Thank you for watching. See you all in the next video. Thank you.